Okay, another day, um another set of lead code questions to do. My life is so fucking happy right now. I mean, I'm doing lead code on a Saturday. Yes. Yes. I love my life. Okay. Let's get this done. So, in the previous episode, I was doing linked list, and I remember that I did not take off this LRU cache because I wanted to do it again just for practice. And I want to do this also, reverse nodes in K group. So, first, let's get these two done. Let's refresh this. Okay. So we need to implement an LRU cache using a doubly linked list. That is the question. So we just need to create a node for a doubly linked list and create two dummy nodes at the head and tail, because that will make it way easier to, you know, do stuff. And yeah, that's about it actually. So let's create one node, which is a struct. In here we need key, we need value, we need the next node, and we need the previous node. Let's create a constructor with key, value, right. In here we need the capacity. This capacity equals capacity, and we need to initialize the LRU cache using this node that we created. So node, okay, we also need head, tail. This head equals new node minus 1 minus 1, head next is tail, tail prev is head. In here we also need to assign these as null pointer. Yeah. Apart from these, we also need a map that will simply unordered map that will simply map the key, which is an integer, to the node in the doubly linked list. Let's call this map or data, right? We don't need to store head and tail because these are just dummy nodes. And then in get, we need to check if key is present in the map. So if data.find key is equals data.end, then return -1, which means not found. Otherwise, if that is found, we need to put that node to the front of the linked list. So node left will be data key, right? Node left will be current previous, node right will be current next. First we attach left and right, and then we need to put current after head, right? Or no, I think put should be doing that. I mean, we don't need to duplicate any operations here. So here we simply need to check if data dot find key is not equals data dot end, which means it is in the data, so we need to remove. Okay, I think a private function remove will be doing the removal of a node from that linked list. So if we are given a node, we just need to remove that. How do we do that? We'll do this left and right thing over there. So instead of this will be node, right? Delete node, just free that value, right? So input, we simply say data dot erase key. Oh, we need to get that found equals data key, data dot erase key, delete found. Then input, we need to simply say new node equals new node key value. Then we need to put it on the head, right? So head next should be new node previous should be head, and okay. Okay, let's new node next is head next, and head next prev is new node, right? New node prev is head, and head next is new node. And we also need to put this in our data dot data key equals new node. That's all. Let's take a look. So we created a node for doubly linked list. We have a next and previous along with key and value. We have a constructor that initializes this key and value. Then in our solution class, we have a capacity. So we are not checking capacity right now. Right, so we can do this here. Simply say if data dot size is greater than capacity, simply remove tail prev. Okay. If data size exceeds capacity, then we get that node from the tail. We erase the data from the map. Then we remove that node from our linked list, and remove should not free the memory actually. So instead of doing a delete here, we should not focus on that. It just removes from the linked list. It just picks that node from the linked list and gives and it stays there in the memory, and we free that memory afterwards. Okay, let's focus where other, yeah, remove current, delete current, put key val, right? Okay, let's see it again. So we have capacity, we have head, tail, and data. Yeah. So in remove, We are just removing that node from the linked list. First of all, let's see the constructor. We are initializing the capacity, then we are creating a dummy node head, we are creating a dummy node tail, head next is tail prev is head. So they are connected. Pradeep Pal, hello brother. How's it going? Okay, in get we try to find that key in our map. If it is not found, then return -1, right? Otherwise, means if it is found, we get that node, we get the value, we remove that node, we free that node, we put that node, and we return the value. Then input, if it is found in our data, we get that node, we erase from the data, we delete, we free that memory, right? Then we create a new node with that key value. We assign it, we put that into the map. Then we do the linked list operation, new node next, head next prev new node prev head next equals new node, right? If data size exceeds capacity, then we get the least recently used, which is tail prev. We erase that from our data, we remove that from our linked list, and then we delete LRU, right? Okay, let's see if this works, man. Okay. Okay, delete found data dot erase key. Found, delete, found. What? Attempting double free. So data dot erase deletes the node as well. Are you trying to tell me that, brother? Is it? Let's see what I did earlier. Okay, we have an insert and remove. Oh, insert and remove. Yeah, why are we deleting this here? No. Remove data key, delete data key. Oh. Data dot erase LRU key, delete LRU. Oh, we haven't removed this yet. Makes sense. Okay, let's write an insert function also. Node so node next is first prev should be node, head next is node prev is head. Okay, let's see here now. If it is not found, then return -1. Otherwise, why are we deleting? Node current equals data key, remove current, insert current, return current value. Now input, if it is found, remove data key, delete data key. Yeah. So we also need insert function, which will make it way easier. Right. Makes sense. Okay. Good enough. The next one. Reverse nodes in K group. Okay, let's see. Given the head of a linked list, reverse the nodes of the list K at a time and return the modified list. K is a positive integer and is less than or equal to the length of the linked list. If the number of nodes is not a multiple of K, then left out nodes in the end should remain as it is. You may not alter the values in the list's nodes, only nodes themselves may be changed. So, okay. So if head is 1 2 3 4 5, I mean if the linked list is this and K is 2, so we pick the first two nodes, we reverse them and then put it here. We pick then the next two nodes, we reverse them and put it here. Okay. Cool. Okay. I was just seeing my stream analytics. No worries, okay. Okay. So the point here is it can be a recursive function and we can do some shit there. I think, yeah, that's the only way. Right? Can you solve the problem in order of 1 extra memory space? Oh my god, bruh. Can I? Let's see. Copy image. Paste it here. So, this is 0, 1, 2, 3, 4. I keep track of this head, right? I get to the tail, like how many, like what's the size of the linked list that I want to reverse. I have the head and the tail, right? Then I can yeah, I can keep track of the next node also, maybe. Or is there any catch here? I mean, yeah, it feels like a loop might also work, you know, because recursive will increase the space complexity. I keep track of 0, then I move 2, 1, 2. I get the tail, I also get this. Then I simply say that reverse from here, and previous is this. So prev initially becomes 3, head or current will be 1, right? And that's all. Let's call it end also. End. So is there any simpler trick here? I don't know. I'm very tempted to look at the solution. Current is head, count is 0. While current and count not equals k, current equals current next, count plus plus. What? Current equals count not equals k, current equals current next, count plus plus. Okay. So count becomes 2, current equals reverse k group current k. Oh. Reverse k group current k. While count minus minus temp. But this is recursive, right? And this is very slow also. Is it? I mean, I get it. I get the point. So we simply say Andrew Karev, what's up, my brother? Keep going, yes, sir. How many have you solved, brother? LeetCode? Okay. $105. Your speed is too good, man. You're doing pretty good. That's not good to hear. Okay. So if I'm trying to, let's see if prev is null pointer or something. When I am at the, let's consider this 5 doesn't exist here. Right. So it is null pointer and it will just return null pointer, right? So head will be null pointer here. Then I'm at current here, right? Then I say while count minus minus, which is 2. I see this will be the next node, and prev is my, let's say this is my prev. Then current next equals prev, so 3 becomes prev. Prev equals current. Prev moves here and current equals next node, which is 4. and prev 4, it will be like this, right? And then I return 4. Yeah, I need to return 4 at the end, so return prev. So should I just call it prev and move on? Will that be fine? Return prev. Is it? Is that it? No. Oh, count. No. List node. Oh shit, one more. Return prev. What? Should I keep here? Nope. See, okay, TMP. Okay, what? Current equals reverse K group. What the fuck is head? Oh. Are you still solving leetcode every day? Not every day. I mean, I took a two-day break, so it's not every day for sure. But I am trying to be consistent overall. Yeah, that's all. I'm not solving every day. It's just, I don't know, fries my brain. So yeah. But I don't miss like 3 days in a row. That's my game plan. So yeah. Okay, so current will be head here. Then current get updated here. So this is probably prev, right? I get the TMP, which is next node. Head next equals current. Yep, current equals head equals temp. Head equals current, which is prev, and then I return prev. Right. If I name this as prev, then it makes more sense. But yeah, still. Yep. Okay. But what is the space complexity of this? Order of n by k. Let's look at short but recursive Java code with comments. Let's see the most voted non-recursive. Yeah, I mean, we can do non-recursive. So we have a dummy node. Dummy next is head. Okay, before dummy, after head. Current null pointer, previous null pointer, next null pointer. While true, cursor equals after. For I equals 0, I is less than I is less than ki plus plus. If cursor is null pointer, return dummy next. Otherwise, cursor moves forward. Then current becomes after. Yes. Previous becomes before. Yes. Then again with k we just reverse it, right? Next equals current next. Yep, current next equals previous, previous equals current, current equals next. Okay. Then after next, which was the head, after next equals current. Right. Before next equals previous. Okay. Before equals after. This is also recursive. Let's try iterative, man. Fuck it. Okay. So if I refresh this, so first of all, simply let's create a reverse function which will simply reverse a linked list, right? Reverse. If we are given a head and we are given a prev, and k, right? Let's see if we can make use of this, or we can modify it further down the road. So we have a head pointer, right? Okay, let's create a dummy node just in case. Okay, then okay, right. For I need to move the cursor, which is current node here. Let's call a cursor equals head. For int. Okay, let's do this. Cursor equals cursor next. Okay, I need to attend a phone call. I'll be right back, guys. Just give me 5 minutes. I'll be back. Okay. All right, I'm back. So, we were on iterative solution. Yeah, when I move this cursor, right? Let's get this cleaned up. I'm at here, cursor, right? And there is a dummy node here. D dummy node. Cursor moves how many steps? It moves k steps. So 1, 2. So cursor becomes here. And I want to reverse this. Right? They should go here. Now. So prev should become cursor, right? And then reverse from dummy next. Okay. What? So I want to reverse from dummy next, so it will become right, but I want this to be here. Okay, I see why this is hard question. Use a dummy head and LR define reversing range. Pre and cur used in reversing. Standard reverse linked list method. Jump used to connect the last node in previous k group to the first node in the following k group. So we have a dummy equals jump equals list node 0. Dummy next is L equals R equals head. Okay. While true, count is 0. While R and count is less than k, R equals R next, count plus 1. If count is k, then pre cur equals RL. Pre is reverse, right, current is L. Okay. Okay, let's see. So we have a dummy node right here. Dummy next is head. Then we have left equals head. Right is also head. To determine the range of reversing. Okay. Then while true, int count equals 0. While count is less than k, while right and okay, if count is k, then prev equals right, current equals dummy next, left, right, left. For current what current next equals pre, current equals previous equals current. What the fuck? Previous, current next. Okay, current next equals prev, current equals current next. No, previous equals current. What the fuck? That doesn't make sense. So as per this code, I have a dummy node here. Dummy next is this, left is here and right is here, right? Because when count is 0, right comes here. When count is when count becomes 1, right becomes here. When count becomes 2, count is 0. Yeah, count becomes 1. Yeah, count becomes 2, it exits. Yeah, so right is here. Then in here, what we are trying to do, previous equals right. So this is previous and this is current. I equals 0, I is less than k. Current next equals previous. So 1 next becomes 3. Current equals current next. We can't go to 2. Yeah, 2 becomes inaccessible. What the fuck? I need to ask chat. How does this evaluate in Python? Okay, next node, current next. Okay, standard river. So like how, why, who, what? Isn't that just bad? I don't know. Hello brother, I can't watch this right now because I have a class now, so we will meet again. Alright, that's fine brother. Enjoy the class. Okay, so we need list node next node equals current next. Isn't this just this? Okay, then after reversing, jump. Okay, connect 2k groups. Okay, jump next, jump and L. Temp next equals pre L and R. What? Jump next. What was jump? Jump was dummy. Oh. So jump next is previous, which will be what? So this becomes this. 2 points to this, right? Yeah, right? Yeah, this becomes previous. So we are saying jump next. Jump Next becomes prev. Jump becomes what? Left. Oh, Nelly. What? Bruh. Jump next equals previous. Left is not moving anywhere, right? Or is it? Jump equals L, L equals R. Yeah, prev will be this. So jump next, which is dummy next, becomes this. Dummy becomes, jump becomes left, which is this. Oh. And left becomes right. Jump becomes left. Left becomes right. Else, if count is not k, then we simply return dummy next. Okay. Cool. Okay, let me understand this thoroughly. Should I use a fucking notebook? Maybe. Okay, so this is not required anymore. So we create a dummy node, which is, okay, let's create a linked list, man. 1, 2, 3, 4, 5. Okay, we create a dummy node D, which is this. Then we create a jump node, which is same as dummy node initially. Then we say dummy next is ahead. We have done that, and left and right are at head. So left is here and right is here. Then what do we do? While true, int count is 0. Count becomes 0. Count becomes 0. Then what happens? While right is not null pointer and count is less than k, then right becomes right next. So we move right by k number of steps. So right here k is 2. Just to be clear, k is 2. So right moves 2 steps. So right comes 1, 2. So right will be here at the end of this loop. Count will be 2. No need to worry about that. Yeah, we can write. So this becomes 2. Now, if count is k, that is correct. Previous equals right. Okay. Now, this is previous now. Okay. And current equals left. Makes sense because, yeah. Now, we simply do a basic reversal, right? This is just previous. So, current next will be previous. So, this will go here. Current will move here. Previous will move here. Then current next is previous. Previous will move here. Current will move here. So this will be the final position of current and previous. Previous will be at 2. And this won't exist. Yeah. So our linked list will look something like this. In first K group reversal, right? Right. So current is at the start of the next K group. Previous is at the head of the reversed K group. First reversed K group. Right. So what do we do next? Jump next is previous. Makes sense because this should be pointing to the head. So jump next. We see right this guy. This next becomes previous, which is just same as this, right? Because they are just copies of each other. So essentially what we are doing is so the dummy node next becomes this. We don't need to carry jump here, right? Becomes previous. Jump becomes left. Okay, now okay, we needed that jump actually. Jump equals left. So our jump node will be at this position. And what position is this? So if I try to okay, this is fine, right? Dummy is here. Dummy next is this 2 1 3. Jump becomes the end of the first K group, right? Yes, because we want to because previous will be the head of the first reversed K group, so that's why we move jump to the end of that K group, because we want to do the linking. So jump acts as the link between the groups, K groups. Jump becomes left, left becomes right. So we move left pointer to the right because we want to reverse the next one. So if I redraw this linked list again at here, so it'll be, we have a dummy node, then we have a 2, then we have a 1, then we have a 3, then we have a 4, then we have a 5. Where is the jump node? Jump is here, which is just copy of jump node is here. Left and right are here. So what state are we in? We have just reversed the first K group, right? Yeah, 2 1 3 4 5. And at the end we return dummy next. So dummy is always at the same position. And jump acts as the end of the reversed K grouped linked list. Acts as the end of the reversed K side line. Yep. Come? No come here, brother. Did I say come at any point of time? I didn't mean that. but you never know, brother. Okay, so makes sense. Then we repeat this process again and again. Okay, let's take a look at this code once again. So we have a dummy node, we have a jump, then dummy next is head, left and right. While true, we count the right steps. If it satisfies, then we say current is left, previous is right. Up until here it is fine. Up until here also it is fine because previous becomes right. Yep. This is the only crucial step that we need to take care of. So jump next becomes previous. What does this do? Jump next equals previous. Connects the end of one linked list to the head of the next linked list. Move this to the end of the reversed linked list. Move left pointer to the next k group. Otherwise, yeah, this is the only crucial step that we need to take care of. That's all. Okay, and iterative might be a shout. Let's take a look at the recursive one as well. So we have a current head count. We count the steps. If it satisfies, previous reverse k group. Yeah, this basically is the start of the reversed k linked list. While count minus minus, standard reversal, and then head becomes prev. Makes sense. Cool. I might need to keep this unchecked because I want to revisit this again. Okay, cool. So linked list seems to be completed. What should I go for next? I hate greedy problems, so okay, let's do tries, or sliding window. Sliding window. Let's do tries, man. Fuck it. Implement try prefix tree. Very basic. Is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure, such as autocomplete and spell checker. Insert search starts with. So try, as far as I remember, is something like this. We have a head node, which is the start of the try. Let's call it T. Then we have 26 children because there are 26 letters in the English alphabet representing each letter. So A, B, C, D, E up until Z. And these letters are present if a word has been inserted starting with that letter. So for example, if apple is inserted, so it will be P, P, L, E, and that's it. So every node has an array of size 26 where which is just okay, so it is basically a vector of try node, let's just call it node pointers of size 26 v. Is it? Initially everything is null pointer. So what will be the structure of this node? I mean, let's define this node. Struct node. Do we need a value here? I don't know. So it should be simply a vector of node char value next of size 26, initially null pointer, something like this, right? Char value, I'm not sure if we want to keep, because from here we can check what character is it just by adding a to the index, right? I think this might be just the thing. We can keep this. Okay, let's see. So we have this, right? The value of this will be anything like asterisk or something. Then next node will contain another nodes. Yeah, we should keep the value. We should. So char value will also be there. Right. So when we want to insert, we go character by character of the word. If it doesn't exist, we create a new node with that value, with that letter. Right? And then we move on. Search. We go, if it exists, then we return true, otherwise false. Starts with, we go to the prefix. If there is something there, then return true, otherwise return false. How do we define end of word? That's also we need to keep track of. Like, so let's say app is also a word, so apple is also a word and app is also a word. So we need a marker to say that, yeah, this is end of word. So instead of this, we also need is end of word, right? Something like this. I am trying to just recall what I learned previously, like 2 years, 3 years ago. I can take a look at my website. So if you guys are not aware, let me go to that channel, man. If you head on over here to my channel, you can find the website link here, bigbraincoding.pages.dev. Here I have a bunch of notes for all of the DSA and algorithms, stuff like that. Let's see tries here. What is a try? Prefix tree. It is a type of search tree in which characters are stored at each node. Words can be retrieved by traversing down a branch. Each try has an empty root node with the links to other nodes, one for each possible alphabetic value. Each node contains an array of pointers to child nodes, one for each possible alphabetic value. The size of the try is directly correlated to the size of the alphabet being represented by the data structure. Every node in try, including the root node, has at least these two aspects: a value which might be null, an array of reference to child nodes which also might be null. So I have a CPP file. Let's see the implementation. Try node. We have a try node. Children is EOW. Yeah. So value is not there. Interesting. That is interesting. Value is not there. That is very interesting. Okay. And is it a class or is just a struct? Class makes more sense. Okay, class try node. Here we have is EOW, and we have a vector of try node. Let's call them children. Okay, just a basic constructor. So for I equals 0, I is less than alpha bet size. Okay, what's the alphabet size here? Only lowercase English letters. Okay, makes sense. I plus plus. Then children of I is simply null pointer. And is E W is false. Cool. With this try node, we can have a try node root, and in this we can simply say equals new try node. That's it. Okay, now in insert we have to say that try node current equals root for every character C in a word. If current of C minus A is null pointer, then current C minus A new try node current equals current C minus A. Right? That's it, right? And at the end okay, current is EOW will be true. And now in search, try node current equals root for char C in word. I can do this. My name is Jeff. For every character in that word, if current what the fuck am I doing? If current children of C minus A doesn't exist, right? If current children C minus A is null pointer, then return false. Otherwise, current equals current children C minus A. Return true. Return current is EOW, right? Because we need to find that exact word. And this will be the same here. We just need to say if it exists or not. True. That's it, right? Root equals new try node. It should be public, brother. What are you doing, man? Fuck. Children is a private member of try node. You know what? Fuck it. Everything is public, man. What? Oh. Prefix, man. Okay. Reference binding to null pointer of type this. What the fuck happened? Reference binding to null pointer. Crawler for int I is this key. Get the index w of I minus a. If crawler is null pointer, then equals try node crawler children key. Yeah, pretty good, pretty much the same. Then in crawler we get the key, crawler children key null pointer, return false, otherwise go there. Yeah, print all. Insert and search. Have I not done prefix? But there isn't any prefix here, man. What the fuck is happening? Reference binding to null pointer of type try node. What? Root equals new try node. Try node current equals root for every character. Then we check the children of current c minus a. If it is null pointer, then current children c minus a equals new try node. Current equals current children c minus a. What? Then in search, current equals root again. Then every character in this word, current children c minus a. If it is null pointer, then return false. Otherwise, current equals current children c minus a. Return current is EOW. Is end of word. Yeah. Current equals root again, character in prefix. Current children c minus a equals null pointer return false. Current equals current children c minus a. What the fuck is happening, bro? Is it something bad here? Vector trinode children. Oh, I didn't define the size. Fuck off. Shit. I didn't define the size, man. Shouldn't be just fucking alpha bet size and null pointer. Isn't this just enough? Oh shit. This is EO. W equals false. Search app, insert app. Insert add character APPLE. Going A, going P. Yep. Search app going A, going PP. Searching prefix app going A, PP. Inserting app. Inserting app. Add character P. Add character P. What? Why isn't it adding character A, bruh? Interesting. Why is it adding character when they are already added here? Let's see. If okay, what happened? Oh shit. If it doesn't exist, then I move, bro. Yeah. Okay. Okay. Searching. If it doesn't exist, then return false. Otherwise, move. And then in prefix also. If it doesn't exist, then return. Otherwise, move. Yeah. This should work. I mean, yeah, okay. Let's see. This might be the last question of the day. Yeah, it works. All right. So that was try. I'll do this. Do these two offline maybe, and I need to study that linked list last question again. Okay, so that will be the homework for today. I'll see you guys next time, maybe tomorrow. So until then, take care and bye bye.